Hello everyone, I am Muhammad Arafat Kabir. I am presenting my paper Coupling Extraction and Optimization for Heterogeneous 2.5D Chiplet-Package Co-Design. This work is supported by National Science Foundation. I am currently working as a research assistant in the EEDA lab at the University of Arkansas. I am pursuing my PhD under the supervision of Dr. Yarai Peng. My research interests are in electronic design automation and VLSI designs. In this post-Moore era, transistor scaling and chip scaling are saturated. However, the demands for increased functionality and performance are ever growing. To accommodate the increased functionality, chips are getting bigger and reaching the reticle limit. Industry has adopted system-on-package design approach to overcome this limitation. Though traditionally PCB is used as the system integration platform, it has drawbacks like high inductance and capacitance, limited bandwidth, and severe power loss. In recent years, 2.5D and 3D packagings are gaining popularity because of their features like high bandwidth, energy-efficient communication channels, and compact sizes. 2.5D packaging further offers new design capabilities like application of novel design techniques, hardware and IP security through obfuscation, and heterogeneous integration. To support 2.5D integration, industry has developed number of high-density wafer-level packaging technologies like EWLB, Swift, and Info. In these high-density packages, the package and chiplets are so close to each other that the interactions between them become significant. These interactions need to be considered carefully in design and optimization steps to implement a fully optimized and high-performance 2.5D system. Currently, there is no standard design flow that can address these issues and take full advantage of the design capabilities offered by 2.5D packaging. We developed our holistic flow for homogeneous and in-context flow for heterogeneous 2.5D systems that can fulfill these needs. In the work presented in this paper, we apply our holistic and in-context iterative optimization flows on a homogeneous 2.5D system and perform a comparative study between them. We also study our in-context flow on a heterogeneous system and present our findings. Traditionally, 2.5D systems are designed in a die-by-die approach. Each chiplet is treated as an individual design. It significantly reduces the turnaround time. However, as the whole system is not considered together, it cannot ensure the maximum performance and the highest reliability. While partitioning the system into chiplets, as the chiplets are connected through RDL wires, the partition tool needs to be aware of the RDL properties. If not planned carefully, due to its pin-dominated nature, the package routing can get overly complicated, degrading the overall system performance. In the planning stage, chiplet pin configurations need to be adjusted to optimize RDL routing and package floor plan. Post-design analysis tools need to consider the chiplet package interactions to fine-tune the system performance and avoid signal reliability issues potentially causing system failures. A cross-boundary package-aware design strategy is needed that can achieve these chiplet package co-design goals through exchange of sufficient design information between chiplets and package. In die-by-die approach, as chiplets and the package are designed independently in their own design environments, there is almost no exchange of design information between them. As a result, it is not possible to ensure a globally optimized design at the system level. In our holistic flow, we incorporate the scope for exchanging design information between chiplets and the package in planning, design, analysis, and optimization steps. Our holistic flow is summarized in this flowchart. Gate-level netlist is synthesized from the register transfer level description of the system. In the planning stage, partition and package planning are performed considering the complete system as a whole. The gate-level netlist is partitioned into chiplets considering the impacts of package wires on the partition result. In the co-planning step, chiplet pin configuration, package floor plan, and routings are prepared together. Based on the package routing, package wire load is estimated. Signal assignments of chiplet pins are performed based on a greedy strategy. Using this top-level plan, timing budgets are extracted for each part of the design and they are separated into hierarchical sub-designs. These chiplet and package sub-designs are implemented in parallel. Though at this step, they are designed separately in their own design environments, the constraints imposed by the top-level plan are active throughout the process. After physical design, they are assembled together for holistic extraction. As all chiplets and the package are present during extraction, this can capture the interactions among all the components of the system. This extraction result is used to perform analysis of the entire system. The flow doesn't stop here. This is only the first iteration. As the package workload and timing budgets used in the physical design are just rough estimates, there is almost always some room for improvement. We use the analysis result of the first iteration to create new timing contexts for each part of the system and go back to the physical design step for the second iteration. In this iteration, as the timing contexts provide an almost accurate view of the system, each part can be fine-tuned for better performance and higher system reliability. This iterative process can be repeated as long as there is room for improvement. After sign-off verifications, the final designs of the chiplets and package can be sent out for fabrication. To test our flow, we selected a microcontroller system to prepare a proof of concept design. The system consists of an ARM Cortex M0 processor core, 16 kilobytes of memory, and some common peripheral devices like GPIO, UART, timers, etc. The 16 kilobyte memory system has four 4 kilobyte banks. Each bank consists of 4 1 kilobyte memory macro. Such granular design offers flexibility in partition and floor planning steps. For 2.5D implementation, this system is partitioned into two chiplets. We call them the core chiplet and the memory chiplet. The core chiplet contains all the logic blocks and 8 kilobytes of memory. The memory chiplet contains the rest of the 8 kilobytes of memory. We use NAND 45 nanometer process design kit for physical design. As there is no publicly available PDK for 2.5D package design, we mimicked TSMC's info packaging technology by modifying the top routing layers of the chip design PDK. Lower 7 metal layers are used with their original settings for chiplet internal routing. VS7 serves as the chiplet contact pad layer. M8, M9 and M10 are modified to serve as 3 redistribution layers. The width and spacing of redistribution layers are both set to be 10 micrometers. A conventional 2D design of the microcontroller system is prepared as a reference. This design contains all the logic blocks and 16 kilobytes of the memory. Design, optimization and analysis are performed following the standard 2D chip design flow. The planning step of the flow is carried out by our in-house RDL planning tool, which implements our Chiplet-Package Co-planning strategy. Chiplet dimensions and pin grids are determined based on their area and pin counts. Signal assignments of the chiplet pins is performed after package floor planning and routing. Our routing algorithm makes use of short and straight wires to connect the chiplet pins. Based on this routing and the timing report generated through analysis on the gate level netlist, the signal assignment of the chiplet pins are performed. This is done following a greedy approach so that slower signals are assigned to the shorter package wires. The figures show the floor plan and routing generated by our RDL planning tool. Each subfigure shows the routing on only one RDL. Because of the way system is partitioned, all pins of the memory chiplet are connected to the core chiplet and the core chiplet is connected to all the system external I/O. After package floor plan, routing and signal assignments are complete, the RDL planner tool estimates the package wire load based on these information. Based on the plan generated by the RDL planning tool, the top-level plan is implemented in a unified design environment. This environment is set up using the modified PDK, which supports both chiplet and package routing layers. Most part of the package design is also performed in this step using the scripts generated by our RDL planning tool. After implementing the top-level plan, the design is partitioned into hierarchical subdesigns. Timing budgets are extracted for all chiplets and the package subdesign. The package wire load estimated by the RDL planning tool are appended to the design constraints of each subdesign. Each subdesign is implemented independently following the constraints propagated from the top level. Chiplets are designed as if they are conventional 2D chips with additional design constraints. The figures show the finished physical design of the core and memory chiplets. Their floor planning, power planning, placement and routing are performed using standard 2D chip design tools. When all chiplets and the package design are complete, they are assembled in the unified design environment for holistic extraction. The figure on the bottom right shows the assembled system containing traces from both chiplets and package. The extraction tool has all the information needed to capture the interactions among all the components of the system. As a result, it can effectively capture the impact of RDLs on the overall system performance. The table presented in this slide shows the holistic capacitance extraction results in femtofarads. For readability, capacitance numbers of layers M1 to M5 are merged together. In traditional extraction method, it is not possible to get the coupling between chiplet and package routing wires. In our holistic method, these cross-boundary interactions are captured, which are highlighted in red in the table. It is noticeable that though M7 is the topmost chiplet routing layer, the coupling between M6 and RDL1 is greater than that between M7 and RDL1. This is because M7 has significantly less routing wires compared to M6 in the design. The coupling capacitances of M7 and RDL1 are also extracted with cross-boundary considerations. This kind of detailed interactions can only be captured in holistic extraction method. This extraction result can be utilized to incrementally optimize the system for higher performance and signal integrity. To demonstrate the effectiveness of holistic consideration, we study some design cases which are present in this table. Case 1 is the reference 2D design. In absence of package overhead, this is the best performing system. It achieves a system frequency of 333 MHz. Case 2 is a 2.5D implementation designed in the traditional die-by-die approach. Each chiplet is designed and optimized separately. Though each chiplet individually can operate at 333 MHz, due to package overhead, the complete system runs at a degraded frequency of 245 MHz. For the sake of comparison, we take this 88 MHz performance gap as the 100% frequency overhead of a traditional 2.5D system. Case 3 initial is the 2.5D implementation obtained at the end of the first iteration of our flow. In this iteration, estimated package overload, greedy signal assignment, and our co-planning strategy are applied. Even with rough estimation, the overall system frequency achieved is 280 MHz, which is a 40% reduction in the frequency overhead. Case 3 final is the 2.5D implementation achieved at the end of the second and final iteration of our flow. In this iteration, the newly created timing contracts are used in the physical implementation. Further iterations did not improve the system performance. This design achieves a system frequency of 300 MHz, which is very close to the system frequency of the 2D design. That's a 62% reduction in the frequency overhead. These design cases clearly show the importance of holistic consideration in 2.5D system design. Our flow can utilize the holistic extraction result and iteratively improve the system performance. The chiplet design tool automatically optimizes the inter-chiplet I/O buffers to compensate for the package overhead based on the timing context created at the end of the previous iteration. Though holistic flow would be the best to globally optimize and fine-tune a 2.5D system with standard tools, it cannot be used to design heterogeneous 2.5D systems. This is because existing EDA tools cannot handle multiple heterogeneous technologies together in a common design scope. As a result, the design assemble, holistic timing budget, and parasitic extraction steps of our flow cannot be directly applied. That is why we developed our in-context flow that can design a heterogeneous 2.5D system using standard tools with sufficient holistic considerations. In our in-context flow, in the first iteration, timing budgets are extracted using the gate-level netlist instead of the top-level design in the unified environment. Note that Chiplet-Package Co-Planning step is the same as in the holistic flow, because it is implemented using our in-house RDL planning tool that can handle heterogeneous technologies. For each technology, a unified PDK is created, stacking up RDLs on top of the chiplet routing layer. top-level package routing is generated, treating the chiplets as black boxes to avoid their heterogeneity. Then this package design is broken down into sub-regions around the chiplets to create an extended partition for each chiplet. After physical design, each chiplet is individually assembled with its package context, and in-context extraction is performed on it. All the extraction SPEF netlists are stitched together in the analysis tool for timing context creation. These timing contexts are used for iterative optimization and sign-off verification. A little illustration will clarify the concept of in-context partition. As shown here, the top-level package is designed treating chiplets as black box macros. This design is prepared for all the unified technology stacks. Then this package design is broken down into sub-regions, each of which sufficiently encloses the surrounding of a chiplet. We call these sub-regions as in-context partitions. We added an extra level of hierarchy in the gate-level netlist to define these in-context partitions. For in-context extraction, a finished chiplet design is assembled with its in-context partition. Unlike holistic design, this assembled design does not have the complete system, but it can sufficiently capture the interactions between a chiplet and its surrounding package routing. The extraction result of all in-context partitions and the package are stitched together to create a holistic view of the system within the analysis tool. To compare the accuracy of our in-context extraction method with respect to the holistic extraction, we performed in-context extraction on the homogeneous design. This table shows the layer-by-layer comparison between die-by-die extraction and in-context extraction with respect to the holistic extraction result on the homogeneous design. As seen from the green rows, in-context extraction results are very close to the holistic extraction result. The error in both total ground capacitance and total coupling capacitance are less than 1%. On package layers, in-context extraction overestimates the ground capacitance due to the fringe capacitances on the cutting edge of the in-context partitions. On the other hand, die-by-die extraction method greatly overestimates the ground capacitance and underestimates the coupling capacitances near the chiplet package boundary. This can cause serious signal integrity issues. This comparison shows that though there is still room for improvement, our in-context extraction method is sufficiently accurate for holistic consideration and iterative optimization of a 2.5D system. We prepared a proof of concept heterogeneous design using 45 nanometer technology. To simulate the heterogeneity from the design tool's perspective, we used different cell libraries and different number of chiplet routing layers to design the two chiplets. This way, we can compare the heterogeneous design with the homogeneous design prepared using the holistic flow. The package routing technology is the same and uses 3 redistribution layers. The core chiplet uses 7 metal layers and NAND gate cell library. The memory chiplet uses 6 metal layers and GSCL cell library shipped with the 45 nanometer free PDK technology. For each technology, a unified PDK is created, stacking up the package routing layers on top of the chiplet routing layers. We denote the core chiplet unified PDK as 7M3R and the memory chiplet PDK as 6M3R, which are based on the chiplet metal layers and redistribution layer counts. The heterogeneous 2.5D design is completed following our in-context iterative optimization flow. This table summarizes the performance of the 2.5D system achieved in each iteration. The initial iteration with estimated wire load achieves 281 MHz system frequency, which is same performance as that of the initial iteration of the holistic flow design. The final iteration of in-context flow achieves a system frequency of 298 MHz, which is as good as 300 MHz of the final design of the holistic flow. This comparison establishes our claim of sufficient accuracy of the in-context extraction method with respect to the holistic extraction. In the conclusion, we can say that holistic consideration of chiplet package interactions is very important to design a globally optimized 2.5D system with sufficient reliability. Our flow can effectively capture the impact of RDLs in optimization and analysis steps. It incorporates necessary interactions between package and chiplet designs for holistic planning and optimizations. Our flows can handle both homogeneous and heterogeneous design, making use of existing ICCAD tools to design high-performance systems optimized at the system level. Our future work includes extending the holistic and in-context flows with broader technology choices, study of signal and power integrity with all RC-LM circuit elements, incorporating chiplet package, co-placement, routing, and optimizations in our flows. Thank you everyone for attending my presentation.